several co-authors, will be published very soon. I think it's already available on Amazon for pre-order. And so all the details of the talk can be found in this book. But the story I'm going to tell you is actually a much more general one than I think most people appreciate. Because it is, while I'm going to, all the really great examples towards the end, there's going to be a lot of planar theories and supersymmetry is going to really help us along. The story I want to tell, and what I really want everybody to take away, is that these developments are really general and extend way beyond the special theories in which we've explored everything so far. So just to make that really clear, I just want to kind of outline this connection that now is known to exist, but has only started to have been explored. And it's this connection between on-shell physics, which I'll define, these on-shell functions, on-shell diagrams, we'll talk about that in a moment, and this area, a lot of very interesting things in algebraic geometry, combinatorics, and graph theory that are either new or still undeveloped in the mathematics side. But there's this robust connection between on-shell diagrams and functions. There are caveats here and there, but I think that they're not really all that necessary. But at the very least, for four-dimensional quantum field theories with massless particles, any quantum field theory with massless particles in 4 dimensions, there's a robust connection between on-shell diagrams and certain subspaces of certain Grassmannian manifolds with preferred volume forms. And the fact that there's this one-to-one correspondence is actually extremely powerful. And in the case of planar n equals 4, we've learned an enormous amount in both directions. But we're only starting to learn both for more general theories. If you study the volume-preserving diffeomorphisms, you learn about physical symmetries. You could have discovered the Yangian if you didn't know about it from this. This is also interesting on the mathematics side. And it provides a geometric understanding for very interesting physical relations among observables. And so I'm putting this at the top just because I want to make it clear that while these tools we're still learning how to use these tools, and we're still learning how to sharpen them for more general quantum field theories, they exist. Okay? And this is a really exciting ongoing area of research. And so it is true I'm going to stick to n equals 4, planar n equals 4 for a lot of the concrete examples, but that's just because it's the simplest, and it's the one where everything's worked out on both sides. That's not quite true, but a lot has been worked out. Okay. So I'm going to start with a parable, which is a great way of, it's a beautiful, timely story. It's from 30 years ago, this next month. And it's also a great microcosm of the kind of problems, and the kind of, a microcosm of research in scattering amplitudes for the last 30 years. And it's also a way for me to sneak in some definitions of the only kinematical, some of the conventions and notation that I need for the rest. And then we're going to talk about these new objects, these on-shell functions. We'll see how they encode and are related to scattering amplitudes. And we'll see how incredibly powerful this picture, and especially this connection to the Grassmannian geometry, is for the case of planar maximally supersymmetric Yang-Mills, not because they only exist for this theory, but just because it's really simple for this theory. So we'll see that in this case, basically everything you need to know about the theory is combinatorial. It's very powerful. Okay, so let me start with kind of set the stage. Imagine you're in a quantum field theory class and your professor asks to compute the scattering for 2 gluons into 4. Now, at first glance, you'll probably think this is either trivial or impossible, if you don't have a computer at least. The reason is because this process, although fairly simple and straightforward, you just add up all the Feynman diagrams, there are 220 of them. We're talking thousands of terms. In fact, it's so difficult that before the era of computers and machine computing, this was completely out of reach, theoretically. Which is a shame because this process, 2 gluons to 4, happens millions of times a second at the LHC, and it's an important background that you need to know. And if you don't believe me that this was a real challenge and difficult to do, in the early 80s there was a paper outlining the problems that would be faced by a supercollider, the superconducting supercollider, and they explicitly mentioned that no cross-section for 2 to 4 had ever been calculated, and the complexity is such that they might not be evaluated in the foreseeable future. Okay? They were calling for theorists to estimate these things because we couldn't possibly add up 220 Feynman diagrams. Well, there are very few ways of motivating people better than telling somebody that something is impossible. And sure enough, Park and Taylor quickly took up this challenge and threw everything they had at it. So they decided they wanted to calculate this. They could answer that challenge. And they used every theoretical tool they could think of. They introduced an auxiliary supersymmetry, n equals 2 supersymmetry. It was very weird. They used the world's best supercomputers at Fermilab, and as soon as they got the answer, they rushed it to publication. And look at this abstract. Just one sentence. The cross-section for 2 gluon to 4 gluon scattering is given in a form suitable for fast numerical calculation. Okay, and you probably, it's not a short paper, but you've never seen one more brief. Basically, it's just one formula that fits on 8 pages. And you don't need to, read this, but this is what it looks like. These are some coefficients, and this is what the answer looks like. But what I love about this paper, and it's not their most famous paper from that year, is the ending. They chose to end this on this quixotic note of optimism, and I still don't know exactly what they saw in this calculation, but they closed it with this optimistic note that furthermore we hope to obtain a simple analytic form of our answer, making our result not only an experimentalist's but also a theorist's delight. Okay, of course it would be useful to have a simplified form of that equation, but what they could have been thinking when that it would excite theorists, well, it's hard to imagine what they saw, but within 6 months they stumbled upon an answer that must have exceeded their wildest dreams. And it's in a paper that's being celebrated next month at Fermilab, because it's just incredible. So they guessed a simplified form of this expression that fit on one line, but it was better than this. So they guessed the following formula, and I'll explain the notation in a minute. It kind of doesn't matter. 2 gluons to 4 gluons. This is the formula they guessed. And they checked on their computer numerically that this function is the same as that 8-page formula. This is just the pre-amplitude formula. And they also checked that this formula looks that, even before you know the notation, and even to a precocious middle schooler, if you look at this formula, it obviously generalizes to 2 to any number of particles whatsoever. So that's what's truly amazing. Not only is it 8 pages into one line, but it naturally suggests a conjecture, an ansatz, for the amplitude for 2 gluons to create any number whatsoever, and in one line. And if you're not impressed by this, you haven't thought about it hard enough. When 2 gluons create 50 gluons, the number of Feynman diagrams involved exceeds the number of atoms in the universe. Okay? And they're conjecturing that this is this one line. And clearly, this should be, you should appreciate, this is an indictment on our way of understanding quantum field theory. Because clearly we're doing something wrong if the answer is so simple. And there are a lot of culprits, and we'll see how to, by the end of this talk, we'll have derived this formula. So we will prove it. But it stood as a conjecture for about 15 years or so. And I want to point out, I guess, before we go on, it's not really quite in the spirit of amplitudes, but this feature that you break your back calculating something to find something simple is totally ubiquitous in quantum field theory. From the G-2 homework assignment that everybody does, and you find out that it's a half after doing a week of algebra, to scattering amplitudes, to 8-loop amplitudes in n equals 4. Every time you break your back to calculate something, the answer is simpler than you expected. And so long as we continue to be surprised by the predictions made for experiments, we can't truly say that we understand quantum field theory. So in this talk, I think we today understand the origin of this level of simplicity. So there's tons more simplicity still around the corner at loop level and for more general theories that remains to be explored. So let me explain this notation. It's just kind of an excuse to introduce this notation, because it's basically the only notation we're going to need in this talk. So this is actually not the language, the form that they used in their paper, in the Park-Taylor paper, but it actually is an older notation. It goes back quite a way to 1929. Some variables introduced by van der Veerden to describe massless external momenta. So the idea is very simple. So instead of talking about 4 vectors, PA and mu, you dot them into the Pauli matrices, and you get these 2x2 matrices. This conversion is completely lossless and trivial. Notice that for real momenta, this is a Hermitian matrix. And the insight comes from the fact that when you look at the determinant of this matrix, that the determinant is nothing but the norm squared of this 4 momentum. And that means that it is 0 for a massless particle. And so, instead of thinking of masslessness or the on-shell condition as a constraint on the 4 momenta, all you need to do is write a 2x2 matrix with vanishing determinant, and it's very easy to write a 2x2 matrix with a manifestly vanishing determinant. All you need to do is write it as an outer product of two vectors. That will always have vanishing determinant, and we'll call it lambda, lambda tilde. These are the spinor helicity variables introduced by Van der Veer in 29. So this will always have vanishing determinant, and so this is a manifestly on-shell way of describing things. For notation, we're going to associate the lambdas with angle brackets and the tildes with square brackets for a reason that'll become clear in just a second here. And this notation, this dot, just means summing over particle index. So this just means summing over lambda, lambda tilde for all the particles, which means it's a sum over momenta. It's a 2x2 determinant, or sorry, delta function, because it's a 2x2 matrix of delta functions. So this is just ordinary momentum conservation. Okay. One of the reasons for really liking these variables is that they behave very nicely under Lorentz transformations. So the local Lorentz group is SL2 left times SL2 right, and under which lambda and lambda tilde transform in the fundamental representation respectively. And that means that Lorentz transformations have to be SL2 invariants, which are determinants. So the only Lorentz invariants you can construct are just determinants built out of these lambdas or lambda tildes, hence this notation. So if you really like indices and epsilon tensors, the determinant, of course, is just that, but come on, it's just a determinant. And so these are the Lorentz invariants, and out of this you can construct all of your other favorite Lorentz invariants. Notice that this replacement is left invariant by rescaling lambda by anything and lambda tilde by the inverse. This, of course, the set of transformations that leave the momentum invariant, of course, corresponds to a little group. And it leaves the momentum invariant, but it does not leave wave functions invariant. And that's actually going to be useful to us in just a couple of moments. So this corresponds to the action of a little group. It leaves the momentum invariant. But wave functions transform uniformly depending on the helicity of the particle. So if a particle of spin s, this will transform as plus or minus 2s times the wave function. So this is actually going to be very useful to us later on. Okay, so the data that describes massless particles and massless particles, the momentum, the kinematic part at least, is a pair of 2x(n) matrices that encodes all the lambdas and the lambda tildes for the particles. And in terms of this kind of kinematical data, this function is very simple. It's just the product of all of the consecutive minors of this matrix. And it basically doesn't care about lambda tildes at all, except for through momentum conservation. So it's really, up to a momentum conservation, it's just a function of lambdas. And we can think about this in two obvious ways. We can think of it as n column vectors, which is natural often, but it's also natural to think about it as a pair of n-dimensional vectors, a pair of rows. One reason for thinking about it as a pair of row vectors in n dimensions, it's a weird way of thinking about it, but under the action of SL2, SL2 just rotates these rows into each other. And so the Lorentz invariant content, of which the amplitude is a function, is described by a pair of vectors in n dimensions up to rotations. And if you include the little group rescaling, you can also rescale. And so it's basically two vectors in n dimensions, modulo rescalings and rotations, means it's the span of these planes. So the Lorentz invariant content is just this plane spanned by two rows in n dimensions. And it's the first example of a space that's going to come up again and again in this talk. It's called the Grassmannian. So the space of, if you have k n-dimensional vectors, the span of those k vectors is called the Grassmannian of k planes in n dimensions. Or rather, a span of k vectors in n dimensions is an element of the Grassmannian. And that's it. You can think about it as a k by n matrix modulo GLK, or you can think about it as, you can think about it in many different ways. And the kinematical data is kind of like a Grassmannian. That's what it is if you just look at lambda. Yeah.
So is there an easy way to think about how the original momentum translates into this space, or vice versa?
Well, if you think about so the SL2 transformations just act by 2x2 matrices on this matrix, and so which corresponds to rotating these, adding some multiple of this row to that row, and the little group allows you to rescale it as well. So you get all of GL2 if you want. That's a little subtle because you can't do it independently on lambda and lambda tilde. So it's not quite true that it's a pair of planes. But Anyway. But there's one interest, I mean, this is kind of a throwaway comment at this point, because this Grassmannian it doesn't play much of a role, but it does allow us to think about momentum conservation geometrically, which will have one application in a couple slides. So, so geometrically, the fact that lambda and lambda tilde, that they dot into zero, summing over that particle index, means that as two planes in n dimensions, they are orthogonal. That word gets me in trouble. No, what it means is that they're in each other's orthogonal complements. If you have some k vectors in n dimensions, you can talk about the space that's not spanned by those k vectors, which is an n minus k plane. So there's a natural dual between a k plane in n dimensions and an n minus k plane in n dimensions. And the momentum conservation is a geometric statement that lambda is in the orthogonal complement of lambda tilde and vice versa. And that doesn't mean much, but it will have an important consequence when n equals 3, which you can think about now if you'd like, but I'll come back to it. Okay, so the question now, so this is I often wonder why this notation isn't more familiar, but it's kind of obvious why it isn't. So the reason why most quantum field theory textbooks don't dwell on spinor helicity variables, why this is kind of lost to between 1929 and the twistor revolution in the 60s, is basically because the way we talk about physics, our traditional formalism of Feynman diagrams and Lagrangians, doesn't care about on-shell particles very much. It's actually really important to talk about things off-shell. The Lagrangian description requires this, you require virtual particles that are off-shell, and so talking about the external on-shell states isn't very useful for the Feynman diagram prescription. But of course, talking about these virtual particles required by the Feynman expansion that are natural there requires also the introduction of gauge redundancies and ghosts at loop level. And this unphysical baggage that you need to carry around in the expansion, introducing new degrees of freedom that the amplitude, the experimental observable, is not sensitive to in any way whatsoever. And so perhaps that is why the Feynman expansion does such a poor job with capturing this simplicity, is because when you're adding up this 10 to the 90 Feynman diagrams for 2 to 50 scattering, that all you're doing is canceling out all these unphysical degrees of freedom. And so maybe one way to capture this simplicity is to insist on never introducing theoretical redundancies. And this is going to prevent us from talking about a Lagrangian description, but let's see how far we can get. And so one way to motivate this whole program on scattering amplitudes, and most of the developments in the last 20 years, has been to try to see how far we can get. How much of quantum field theory can we reproduce without ever making any reference to virtual particles, ghosts, Lagrangians, gauge redundancies, or any of the other unphysical theoretical baggage that we need to carry around for the Feynman expansion. And that might seem like a tall order, but we'll see that, at least in certain quantum field theories, and probably in many, we can actually reproduce at least all of perturbation theory. Maybe not, well, yeah. How much of quantum field theory is that is a debate for another day. So if we're going to insist on only talking about physically observable quantities, then we have to talk about on-shell momenta, not virtual particles, and the states and the things that describe them. And we're limited immediately to a very small class. It might seem like we're limited to a very small class of functions, because there's one thing that we can talk about, of course, is the S matrix. If you have n on-shell particles, this is something experimentally observable, it's a meaningful function, and we can talk about it. We're allowed to talk about S matrices. But a moment's thought will show that we can actually talk about a lot more than S matrices. There's a huge generalization with the S matrix. Because if you knew any S matrices at all, you could glue them together in a very direct and simple way. So this is not a Feynman diagram, please. I'm going to draw lots of diagrams. This is not a virtual particle. This is the first example of what we're going to talk about, on-shell functions. So the meaning for this as a function of external data and physical data is clearly dictated by basic principles of quantum mechanics, locality and unitarity. So locality, because this internal particle is on-shell, it's a physical particle, it's an observable particle, this process, this amplitude and this amplitude, can happen at arbitrarily separated places in space and time, and therefore locality dictates that they must be independent, and the only meaningful thing to talk about is the product of the two. So whatever the meaning of this picture is, it's got to be the left times the right, evaluated up here. And unitarity dictates that we have to marginalize over all the unobserved states. And for that, it means integrating over the phase space of the Lorentz invariant phase space allowed for the particle I, and summing over all of its quantum numbers. So the felicities, masses, colors, everything else that labels it that's not a kinematical degree of freedom. Now I want to emphasize here, although I put D3 lips and whatnot, this statement applies in all quantum field theories and all numbers of dimensions. Masses, massless, doesn't make any difference. Okay? This is a well-defined operation to take amplitudes and glue them together. But immediately you can also see that not only can we generate this kind of picture, but we can generate arbitrarily complicated pictures, graphs of full amplitudes. They're not, they might look like Feynman diagrams, but they're not. Every line is a fully on-shell particle. So, in particular, if you had a network, some graph of amplitudes glued together, the definition is completely clear. It's the product of all the vertices integrating over the phase space of all the internal particles, summing over all their states. This is I want to emphasize these are completely well-defined things. This might seem like a vast generalization of the notion of an amplitude, but we'll see in a little bit that at least for certain quantum field theories, and probably for all of them, the converse, that actually this class of functions also encodes all amplitudes as well. So, although it looks like we're generalizing amplitudes, I think we're just exploring the same space. Okay. So, one thing at the outset that we can characterize these graphs is how many constraints. Do they vanish for general kinematics? Do they impose delta functions? What is the physical, how many constraints are imposed on the kinematics? And that's very easy to count because the number of delta functions in such a graph is 4 per vertex. There's a momentum conservation at every vertex. So you have 4 delta functions per amplitude. And you have 3 phase space integrals per internal line. So you've got that many delta functions. Now, of course, any network of momentum-conserving delta functions, momentum-conserving amplitudes will conserve momentum across the entire graph, and so it's natural to count the number of excess delta functions. So remove the 4 overall the delta functions of momentum conservation. So and for this graph, n hat delta, it's 4 plus 4 minus 3 is, well, it's 5, and then 4 of which are overall momentum conservation. So this has n hat delta equals 1. It imposes 1 constraint on the kinematical data. This is a distribution on the phase space of the massless particles. Okay, but the general graphs can have n hat delta basically anything. If it's negative, it means that you have some number of integrations. You have some delta. You weren't able to soak up all of your phase space integrals with the delta functions, and that means you have some integrations to do, which, by the way, is good because that's where loop integrals are going to come from. Okay, and if it's if it's 0, you just have a normal rational function. And if it's negative, you have some integrals to do, and if it's positive, you have some number of kinematical constraints. Let's focus for a moment on this when it's equal to 0. So, of course, for full amplitude, it's equal to 0, right? This is just 4 minus 4, 0. The first graph, non-trivial graph, not single amplitude graph that has n hat delta equals 0, that doesn't impose constraints, it might look a little scary at first, but it's not that bad. It comes from the product of 4 amplitudes. Now, some of you might have seen this, and 20 years ago, these were called leading singularities, or maximal cuts, or whatever. Forget about all of that. This is not defined in terms of Feynman diagrams or anything. This is not a loop anything. This is just products of trees integrating over on-shell phase space. And there are 16 delta functions, 12 integrals to do. You're left over with just momentum conservation on the outside. So this is a rational function in general. Okay. And part of the purpose of this talk is to get you more comfortable with looking at these weird-looking graphs. Okay, but a natural question is, so we've now see that if we knew any amplitudes, we could start gluing them together into some complicated mess of higher point functions and things that are free of redundancies. But we don't have anything to, we don't yet know any amplitudes. How are we going to get the amplitudes to feed into this machinery? And it turns out that at least for 4-dimensional theories involving massless particles, like the standard model, for example, there's a very simple place to start, and that is the 3-particle amplitude. Because in 4 dimensions, for massless particles, Poincare invariance, the little group rescaling, and momentum conservation completely fix the amplitude to all orders of perturbation theory, by the way, up to a constant. And I don't really have time to do this in great detail, but let me outline the logic. It's not that complicated. So imagine you have 3 massless particles with arbitrary velocities. Of course, just on general grounds, it's a function of the momentum of the particles. And we know that momentum conservation tells us that this 2 by 3 matrix and this 2 by 3 matrix have to be in each other's orthogonal complements. But wait, you notice that a 2-plane in 3 dimensions has a 1 plane in its orthogonal complement. Right? There's a unique line through the origin that's orthogonal to a 2-plane. And so the orthogonal complement of lambda is just some vector in 3 dimensions. It's a 1 by 3 matrix. It doesn't matter that happens to be it. It's a high school algebra problem to see if that dotted into that equals 0. It doesn't matter. There's a 1 vector. That's what's important. And momentum conservation tells us that either lambda tilde has to be spanned by this 1 plane, or lambda has to be spanned by this 1 plane. So there's no case in which you have generic lambdas and lambda tildes. And notice that in this case, lambda tilde is dictated by the lambdas. Right? It's given in terms of angle brackets, and this one it's given in terms of lambda tildes. That means that just on general grounds for momentum conservation, the 3-particle amplitude has to be exclusively a function of lambdas or exclusively a function of lambda tildes. Yeah, and because it has to be built out of Lorentz invariance, it has to be built out of the angle brackets, or in square brackets in this case. And the little group rescaling uniquely fixes the form up to an overall constant. So I will save you the algebra. This is what the result is. So this is the unique set of a combination of brackets that has the right little group scaling, and same here for arbitrary velocity combinations. Okay, now it might look like you can have this or the other, but it actually turns out that the velocities involved dictate which one you have to choose. And the reason is fairly simple. Already some of you might have been concerned that I said that you can have the lambdas be generic or the lambda tildes be generic, but not both. Remember that for real momenta, you need to have P to be a Hermitian matrix, which means that lambda and lambda tilde have to be complex conjugates of each other up to a sign. So for real external momenta, in R31, lambda and lambda tilde can't both, there is no solution to these equations that don't have them all vanish. Which is another way of saying that in the limit of real momenta corresponds to taking all the brackets to 0. So if you set them all to epsilon, you see that this thing scales as epsilon to minus the sum of velocities, and this scales as epsilon to plus the sum of velocities. And because the 3-particle amplitude has to vanish exactly to all orders of perturbation theory for real external momenta, that means that we want that to be smooth in the limit of real momenta. This is only valid when the sum of velocities is negative, and this one's the only option when the sum of velocities is positive. So it really breaks into 2 distinct cases. When the sum of the velocities is 0, of course, you can combine them. It doesn't matter. So you have these 2 distinct cases. And because this whole argument was just based on little group scaling and these invariants, there is no momentum dependence on the prefactor. There's some number, maybe quantum number dependent coupling constant, but it cannot run with energy or anything like that, because the energy would have to be described out of these brackets, and there's no way to create a combination of these brackets that's neutral under the little group. So this thing cannot run. This is just fixed to all orders of perturbation theory. Okay. I'm waiting for somebody to yell to argue about that, but okay. So you can just look at this for special cases. So if you imagine you had 2 gluons, if you have minus, minus, and plus, put in H equals plus or minus 1, and you find that you get this formula. Look, it's the 3-particle Park-Taylor amplitude. We just derived it. It's kind of trivial, but anyway, we just derived it from first principles. And this is just the parity conjugate of it. And in fact, whenever you have a quantum field theory with just a particle and its CPT conjugate as your only fields, then it's kind of natural to instead write minuses and pluses everywhere, to just write arrows to note helicity flow. So a blue vertex is 2 in and 1 out, and a white vertex is 1 in and 2 out. Then you can get rid of the plus and minus signs. And so this is what the amplitude would be in pure Yang-Mills. But this is well defined regardless of what the particles are involved. So if you wanted to talk about QED, where you have 2 different kinds of particles, you'd have to decorate the lines in some way to indicate that there were 2 different kinds of helicities involved. And this would be the massless electron-photon vertex, which looks so close to what a Feynman diagram looks like that I'm almost never going to draw this ever again, because This is not the Feynman diagram. This is not the off-shell three-point function. This is the on-shell amplitude, the analytic continuation of the on-shell amplitude. And in n equals 4 or n equals 8, in a theory, only in a theory with maximal supersymmetry do you have the property that the external states are related by supersymmetry to their CPT conjugates. And so in a theory with maximal supersymmetry, the plus and the minus felicity gluons are related to each other by supersymmetry, and that means that you don't need to draw the arrows, because there's a single super amplitude of this type and a single super amplitude of this type. And I'm not going to have time to talk about supersymmetry really at all. For people who are not that interested, the only thing you need to know is that what's nice about maximal supersymmetry is that I don't need to draw arrows. And so all the rest of the pictures in this talk are going to be simpler. But if I carried around arrows, all these pictures are well-defined in Fourier-Mills. And if I had wavy lines and and straight lines, I could talk about diagrams in QED. Diagrams are well-defined. But in maximally supersymmetric theory, something really nice happens, which is that you don't need, there's no dependence on the helicity flow in the vertex. So, given these two vertices, and given the rule that we just described for how to glue them together in on-shell diagrams, we can now construct an enormous variety of interesting functions that are all gauge invariant, manifestly supersymmetric, everything else, that are free of any theoretical redundancy. So we could, for example, glue 2 3-particle amplitudes into this, and we get a 4-particle factorization channel, which is the residue of a pole in the Feynman expansion, or in the amplitude, and it imposes a constraint. But we could glue 2 more, and we get a box, and this thing is generally non-vanishing. And I kind of don't want to tell you this, but it happens to be the case that this happens to be the full 4-particle tree amplitude. Okay, it doesn't look like a tree, but it is. Okay, that's not generally the case. The relationship between these things and amplitudes is a little bit more subtle in general. And just to make that really clear, I'm going to draw some uglier ones. It also has nothing to do with planarity or anything. So this thing, n hat delta is equal -2. So this is a 2-dimensional integral to be done. Whatever contour you choose, it's a meaningful function of the physical kinematical data. This is a 4-dimensional integral to be done. And I kind of don't want to tell you this either, but this happens to be the full 4-particle 1-loop amplitude in planar n equals 4. Meaning that you do those 4 integrals on the right contour, and you get the Feynman. There is a contour choice for which those integrals are exactly the Feynman loop integrals.
That's a theory-dependent statement.
That's a theory-dependent statement, and it's almost never the case that a single diagram represents the full amplitude. But we'll see examples where they are. But I could draw uglier ones. This is valid in non-planar Fourier-Mills, and it's something that involves all outgoing particles, so it's something that's 0 in a supersymmetric theory. Interesting. I could draw this thing in QED. This happens to be the tree amplitude too, but that's also an accident. And this diagram scares people. More generally, I can just glue these things in a completely arbitrary way, and you should be able to hand this off to any good undergrad, and they can multiply all the vertices together, do all the phase space integrals, and get an answer. It's a well-defined answer. And in this case, n hat delta equals 0, so you should just find a function, a rational function of all the kinematical invariants. And you do that exercise, and you find that it's this. Okay. Scary looking, but it's a single term. It's not that bad. And this is always the case. Now, in the next slide, I want to, it's not really needed, but this is one way, if I rewrote history, that we could have discovered the Grassmannian representation of these things. Because if you really sat down and tried to calculate these things a few times, you would probably have discovered the Grassmannian just out of frustration. And what I mean by this is that momentum conservation at every 3-particle vertex factorizes. There are 2 different solutions, and in every case, you only care about one of them. And so putting in functions of lambda and lambda tilde doesn't make that manifest. Just writing this delta function doesn't make that manifest. If you put this on Mathematica and asked it to solve all the momentum conservation constraints, it would give you 2 solutions per, well, it would give you some very large number of solutions in which they give you 2 solutions per vertex, and you'd only care about 1 solution in each case. And so just to make life simpler, for converting this picture into some function of the kinematical data, it is natural to introduce an auxiliary set of data. This is not theoretical baggage, but it's some auxiliary space to make life simpler to calculate this. So let me explain. This is the first kind of way you would have discovered the Grassmannian, connection to Grassmannian. Which is just a way to make this very systematic. And it's going to look ugly, but I promise you it makes life much simpler in the big picture. So the idea is that with every single blue vertex, you introduce an auxiliary 2x3 matrix, 2-plane in 3 dimensions, and with every white vertex, you introduce an auxiliary 1x3 matrix. And you rewrite this nice amplitude. This numerator depends on the theory. This is what it would be in n equals 4. But anyway, you can rewrite that if you have a particular theory in mind. And let me explain this equation in just a second. But so you introduce these auxiliary variables, w and b, to represent this. Now let me explain this notation, because this looks scary, much more scary than it probably should be. So first, these brackets here are just 2x2 minors of this matrix. This is 1, 1, 2, minor 2, 3, 3, 1. And these are the 1x1 minors of that matrix. I know it's an overly suggestive way of explaining this. But first, what do I mean by the measure here? So this is both of them are 2-dimensional integrals. So it's the 2x3 matrices modulo GL2 rotations. So what I mean in complete annoying detail is that you pick any 2 columns of this matrix to be identity and then look at what's left. So for example, if you pick the first 2 columns, then minor 1, 2 is 1, minor 2, 3 is B1, 3, minor 3, 1 is B2, 3, and this is what that form becomes. But if you made another choice, you would have gotten this form. Anyway, the form actually doesn't depend on the choice. And so this expression is just a nice way of capturing all possible choices that you could have made to eliminate this GL2 redundancy or the GL1 redundancy. Okay, but in all cases, we have a 2-dimensional integral to do, and we have 2 extra delta functions to do the integral. And in fact, they're very simple. So in this case, we have 2 delta functions which say that lambda is orthogonal to the orthogonal complement of b. And that is a very roundabout way of saying that lambda and b are the same, right? If lambda is orthogonal to the orthogonal complement of b, then the solution to those constraints is that b is equal to lambda. So you put b equal to lambda, this becomes momentum conservation, this becomes the numerator, and these things become the angle brackets. Trivially get the left-hand side. And on this side, if you solve this equation, that w is orthogonal to lambda tilde, you find that it's the orthogonal complement of lambda tilde, and you find the exact same thing here. Yeah.
Two quick questions.
Yeah.
One, can you remind us what the eta is? And 2, are you sort of in some sense going back off shell by integrating out of this auxiliary?
No, everything's on shell, but they're auxiliary. These are completely auxiliary. Right? I've just introduced them, and you can eliminate them immediately. This is an identity, right? I've just taken this nice rational function. I've just introduced some extra.
Yeah, but if I integrated out some off-shell degrees of freedom and got an on-shell answer, can I say that was auxiliary jump as well?
Probably. Yeah, it wouldn't have organized itself in a Grassmannian. Yeah, I mean, this is auxiliary, yeah. But it's not the same as something that's off-shell. It doesn't appear as something that's an off-shell.
It doesn't have an off-shell interpretation.
No.
And the eta?
Yeah, so the eta, I don't want to explain the eta. This is, in order to do that, I have to explain supersymmetry, which I don't want to do. Just consider this whole part in the numerator to be the numerator that you needed to get the felicities right in whatever theory you care about. Okay. This is the thing that does it for n equals 4. Yeah.
Just to amplify Andrew's question, but it sounds like what you're doing here is to introduce new redundancy.
Yeah, this is new redundancy. Absolutely.
I'm quotienting out by volume of this redundancy for the denominator in the case.
Well, that just gets you down to the right form. So there's an extra redundancy. There's a GL2 redundancy here.
Yeah.
But the whole thing is, there's 2 non-redundant degrees of freedom in this integral, and those are completely eliminated by those delta functions. So.
Actually, all this auxiliary junk you put it in usually to make Lorentz invariance manifest.
Yeah.
And you're making some other symmetry that you like manifest. Morally, it is kind of close, isn't it?
Well, I'll tell you what it's doing. And this is not very similar to off-shell, but what it's doing, the reason why I like the right-hand side more than the left-hand side, and I know this depends on auxiliary junk, what's the big difference is that momentum conservation, lambdas and lambda tildes are not completely decoupled. And in fact, momentum conservation is entirely a consequence of these linear constraints on the b's and the b tilde and the b perps and w and w. So now the lambdas are completely decoupled, and you just have linear equations to solve, which makes it really easy to integrate over the on-shell face, to eliminate internal lines and do all of the bookkeeping that you need to do to integrate over all the on-shell face space across the entire graph. Let me show you what this looks like. Well, first, the output of this. So if you have a general graph, you have a bunch of b's and w's, and you glue them together into some giant matrix I'll call C. Okay, and don't worry about this. So there are k rows in C. and it's by n, so it's some k by n matrix C built out of the b's and w's. What is k? K is 2 rows per blue vertex, 1 row per white vertex, and every internal line integral eliminates 1 row. So that's how many rows you have. In terms of if you were doing this in non-supersymmetric theory, it's the number of minus helicity particles you have coming in. The number of incoming arrows in the decorated graph. Now let me show you what this looks like in practice. So let's say you wanted to compute the factorization channel. I know this is a trivial example, but it generalizes.
But before you go on,
Yeah.
the C dot n theta was just the numerator factor we don't want to talk about.
Yes, exactly. I should have put this in part of W omega actually, and ignored it. I'm sorry.
But the main thing that's happening here is the linearization of the constant in terms of
Yeah.
lambda and lambda and C and C per integrals.
Yeah. And that is true for any trivalent, any graph you build out of momentum conserving 3-point vertices. So it has nothing to do with supersymmetry, planarity, or anything else. Okay, so if you wanted to construct this factorization channel, you'd start by introducing a 1x3 matrix and a 2x3 matrix. And you could glue them together. The outer product is trivial. You get a big 3x6 matrix. Okay, not trivial. And now you have to do the on-shell phase space integral for I is equal to I prime. That's going to eliminate 1 row, and the output is this. And the volume form gets inherited from what you started with. You had the dw2 over w2 and dwi over wi. So it was this nice kind of d-log form. That's theory dependent, of course. But you get some volume form that comes from amalgamating these graphs. And this provides you a nice systematic way of writing down the graph in question in this form. This form will have some really nice properties, and we're going to rediscover this in a totally different way towards the end of the talk again. But already at the outset, just from talking about kinematics in 4 dimensions for massless particles, you might have been led to introduce this auxiliary k by n matrix associated with the graph. Okay, so let me introduce one technical tool which will be useful later, but also has some really powerful consequences. And it's really the most technical little bit in the talk. It's kind of trivial, but whatever. So the idea is how to build up complicated diagrams successively. If you started with a simple diagram, there's a really nice way to make a more complicated one. You take any on-shell graph. This is not an amplitude. This is just some graph. And you attach to it what I'm going to call a BCFW bridge. So you make some bigger graph and thereby define a more complicated graph. Now what did we do? We introduced 2 new amplitudes, so 8 new delta functions. We introduced how many new internal lines? 1, 2, 3. So there are 9 phase space integrals, 8 delta functions. That means there's 1 new integral to be done. So this process introduces 1 new degree of freedom associated with this line. And it transforms the momentum flowing into this amplitude in a very simple way. So a hat is just a plus I, or a minus I, depending on how you orient it. And so things transform. It's very easy to solve momentum conservation, which I'm not going to do. And the output is that the new function you get is just d alpha over alpha times the old function you had at this shifted momentum. Notice that you find from this that the deleting this extra line just corresponds to taking the residue around alpha equals 0. So alpha is parameterizing the momentum flowing through this line, which is on shell, and when you take the residue around alpha equals 0, you just delete it. Believe it or not, this simple slide automatically allows us to derive the all loop recursion relations, and at least in planar n equals 4. For all quantum field theories in any number of dimensions with any content whatsoever in n equals at tree level. So this is a diagrammatic version of the proof that was given by Brito, Cotazo, Fang, and Witten 6 months after it was discovered by Brito, Cotazo, and Fang. The idea is very simple. So imagine you have the amplitude. We don't have it yet, but imagine you have it. And you attached this BCFW bridge to it. Now you have a function that depends on alpha, and what you care about is the residue around alpha equals 0. So the amplitude we care about is just the residue around the origin of this deformed thing. Okay? But we all learned in complex kindergarten that the residue around the origin can be traded for the minus of some of the residues away from the origin by Cauchy's theorem. And so we can trade this as a sum of all the residues away from the origin. And I don't need to talk about Feynman diagrams, but I might as well because everybody knows about them. Anyway, we all know what all the poles are away from the origin. They're when a Feynman propagator goes on shell. Okay? And all Feynman propagators that could go on shell can be divided into 2 different groups. Those which, when you cut them, break the diagram in half, which we're going to call factorization channels, and those which, when you cut them, don't break the diagram in half. Those are called forward limits. And so these are the residues away from the origin, just complete generality, but remember, alpha is not equal to 0 here, which means that the diagrams we actually have are these diagrams. And sure enough, in planar, for reasons that I don't want to dwell on very much, this is infinitely robust for planar n equals 4. It's almost certainly true for any amount of supersymmetry in a planar theory. It's probably true in a non-planar theory. It's probably true in general. I bet a year's salary that this is morally true with arrows and whatever in a general theory. But there is a lot of work to be seen how that works. And anyway, I'm not going to have time to talk about the loop amplitudes.
Postdoc or assistant professor or professor?
My current salary, which I guess is a postdoc with a FA title. So I'm going to basically ignore this for the rest of the talk, but it's worth pointing out that this recursion immediately gives you graphs with n hat delta equal to minus 4L. So every single graph that you get out of this recursion, and if you keep feeding it into itself, you just get a bunch of trivalent graphs, right? You just keep feeding this picture into the left-hand side and the right-hand side. And so this gives you an expression for the amplitude in terms of a bunch of graphs, all with 4L extra integrals to do. And if you choose the contours right, and I'm going to skip over this too, if you choose the contour right, you get the Feynman contour. So you get exactly the L-loop integrand, the Feynman integral. But for most of the time, I want to talk about just this leading term and try to build some intuition about it, about how it captures tree-level amplitudes. Before I go to the next slide, it's worth bearing in mind that we can talk about amplitudes with fixed k. This is naturally stratified into different k's, which remember is 2 times the number of blue vertices plus 1 plus the number of white vertices minus the number of internal lines. All right. For fixed k here, this graph is k left plus k right minus 1. So if we look for amplitudes with, say, 2 gluons in and any number of gluons out, so the part-Taylor amplitude, for example, we're looking for things with k equals 2, which means we need k left plus k right to add up to 4, or to 3. Okay. This is going to immediately imply something amazing, which is that the recursion relations immediately give you the part-Taylor formula for all 2 to any number of processes. And the argument is actually very simple, and it really only involves one non-trivial step. So let's look at the 4-particle amplitude. So k equals 2, so we have to have left and right add up to 3, and we only have 2 and 1 for the 3-particle amplitudes. So we have a blue and a white vertex, and you can do it this way or that way. Now, remember that the white vertices tell you there's a constraint on the lambdas, that all these lambdas are parallel to each other, and also here, which means that this tells you that lambda 1 and lambda 2 are proportional to each other, which is a kinematic constraint. So this, although you can draw it, and you can include it in your calculations, this thing vanishes for generic external momenta. And so you should throw it out. And in fact, whenever you have a 3-particle k equals 1 vertex on the left, you have to throw it out, or k equals 2 vertex on the right, you should throw it out, because both of those impose constraints on the kinematics. So there's one term that survives. You might not be impressed by that, but anyway, it's one term. I should point out it's not all possible graphs like this, because, and it depended on, notice at the bottom is stayed the same. The recursion relations require 2 arbitrary choices. First, a choice of which legs to use, 1 and n, and also whether you use white-blue or blue-white. Both of those choices are arbitrary and affects the graphs you get in the answer, but it doesn't affect the answer. So this depended on this arbitrary choice of 1 and 4, but if we had chosen 3 and 4, for example, instead, we would have gotten this graph. And these two things are both the same, and they're both the tree amplitude, which I had mentioned earlier. But let's look at a less trivial example. So for n equals 5, k equals 2. The only way to distribute the k's is have amplitude on the 4-particle on the left, and then this white vertex on the right. And we just feed the recursion into this picture. So we just glue that picture in there, we get this. I know it's a weird-looking graph. 6 particles, we get an even weirder-looking graph. But I want you to, what you shouldn't forget is that this is one term. And in fact, for any 2 to any number of particles, which corresponds to k equals 2, you always get one term. And it's an ugly-looking graph, but it's easy to show that this is exactly the part-Taylor amplitude, regardless of that. So we've immediately captured that amazing simplicity and proven it. But it actually encodes a lot more simplicity too, because it captures amplitudes like the 3-to-3 process for 6 particles that I don't think anybody was expecting a Park-Taylor-like expression, but we immediately find really concise formulas for all those other amplitudes as well. So for the 3-to-3 amplitude, you get, it's k equals 3, so k left plus k right equals 4. Anyway, you get these 3 pictures, and you feed the recursion into itself, and you get those pictures. And it's actually in terms of these pictures that these recursion relations were discovered, kind of experimentally, phenomenologically maybe, by Brito, Cachazo, and Fang, before they were proven in general. Yeah.
So your formulas look cyclically symmetric.
Yeah.
But these pictures don't look.
Totally not cyclically symmetric. And it depends on this all sorts of weird choices. I had to choose, not only did I need to choose 1 and 6 at the beginning, but I needed to also choose which pair of legs I wanted to use for this recursion. So there's tons of choices. And I need to get lots of different graphs. And this is a very important point, because one of the most salient things I want to emphasize about this is that there isn't a formula for the recursion relations. You get, depending on which choices you get different graphs, you get different functions. They don't look cyclically symmetric or anything. And it's very non-trivial that it's cyclically symmetric. So first, there's many different BCFW formulae, and they're generally different. And in this case, if you had just chosen legs 1 and 2 instead of 1 and 6, you would have gotten these 3 pictures. I know they look the same. They look just simply rotated. But none of these 3 functions, these are all rational functions, none of these 3 functions are equal to any of those 3 functions. And the fact that these 3 functions equal to those 3 functions is a really non-trivial functional identity. And it's really hard to see at just at the level of functions. It's a consequence of Cauchy's theorem, but it really wasn't until we had the Grassmannian and ultimately the amplituhedron that we understood that there was a geometric origin of all of these things. These were chopping up some volume into canonical pieces in lots of different ways.
So at this point, there was no Grassmannian. You could have said all these things by just looking at the...
Yeah, as it was. I mean, this was discovered in 2004, and Grassmannian not until 2007 or 8 or something. Yeah. We were going to rediscover the Grassmannian in just a moment, in a different way, but yeah. So, but one reason why you probably didn't see these pictures in the physics literature for very long, why they pretty much disappeared as soon as Witten had his proof, had a more general, not diagrammatic proof of this, is because it was clear at the very beginning that these pictures have a lot of redundancy attached to them. And the easiest way of seeing that, and this was noticed in the original paper, the discovery paper, is that these 3 functions, all the graphs look pretty different from each other. They're all basically the same function. What I mean by that is that this function is the same as this function with all the indices rotated by 2, and same here. So although this graph is not a rotation of this graph, the function is. And so there's clearly something else going on that you're missing in these pictures. And it's ugly to draw pictures. Even though there are fewer of them than the Feynman diagrams, there's clearly excess redundancy here, just in the way we're drawing them. So it's natural to wonder at this stage, what is the invariant way of characterizing these functions? How do I know that this thing rotated by 2 is the same as this function? And also wishful thinking, is there a better way of computing them than gluing together all these little Grassmannians to each other, which is probably the best way we have up to this point in the talk. Better than the old-fashioned way. But the old-fashioned way, of course, is well-defined. Multiply all the vertices, integrate the internal phase space. Okay, so it turns out that the answer to this question for planar n equals 4, where there's no arrows anywhere, is so incredibly beautiful. It's kind of astounding that nobody noticed it until a few years ago, 2 or 3 years ago. And the basic point is that there's only there are only 2 ways of manipulating a graph that leave the function on the outside invariant. And they're very simple, easy to understand. The first is that if you have a chain of same-colored vertices inside the graph, that this function, a non-shell function with this in the middle and this in the middle are identical, because they all basically tell you that the lambda tildes of these 4 lines are proportional to each other. And if you want, you can therefore define a 4-valent vertex if you wanted, and make all the graphs bipartite. I won't do that because I like the trivalent graphs, but anyway, you could define bipartite graphs if you wanted to. But the less trivial identity is related to this 4-particle tree. Remember that this box is the same as this box, which means if you go inside a graph and you just change this box to this box, you leave the function on the outside invariant. And so what we're interested, and these turn out to be the only physical identities, and also has nothing to do with planarity. These are the only two identities we have in this graph, in this space of functions. So the question is, how do you characterize the graph modulo these moves? And it turns out there's a beautiful, beautiful, simple combinatorial answer to that question. The idea is the following. You start on you associate with any planar graph with two colored vertices a permutation defined as follows. You start at leg A, and you go into the graph. And when you see a white vertex, you turn left. And every time you see a blue vertex, you turn right. And this is guaranteed to get you out of the graph. To prove it, just remember that you can reverse the direction of the graph by changing blue to white. Okay, so everything is the terminus of something. Okay, so this defines a permutation among the external labels. And this permutation is left invariant by these moves. This is very easy to see. This one being fairly non-trivial. So we know that this permutation label attached to a graph is left invariant. And amazingly, at least for all the graphs that we care about in this talk, there's an asterisk attached to this, but for the purposes of the talk today, the converse is also true, meaning that if you have two graphs labeled by the same permutation, they are related by moves. So it means that the invariant content of the graph is encoded exactly by this permutation label and nothing else. And it means you can get rid of the graph, maybe. So, remember I claimed that this function was the same as this function with rotated labels. All you need to do, because this is a case where the converse is true, all you need to do is just check that their permutations match. So 1 goes to 3, 2 goes to 5, 3 goes to 6, 4 goes to 1, etc. Because their permutations match, they're the same functions. And of course, you're now all wondering, can you get rid of the graphs? But clearly this whole function is characterized by the permutation. What's the graph doing for you? And to show you that everything about the function and the graph and everything is encoded by this permutation alone, we can do this constructively. I will show you in just a moment how to take this permutation and immediately write down a representative graph and the function. And this is an extremely combinatorial procedure, which means that at this point, you can now define the entire recursion relations for planar n equals 4 just as operations on permutations. And this allows you to go to very high multiplicity, very high loop order, just by writing down lists of integers in planar n equals 4, which is amazingly powerful. So there's a technical point which is maybe worth mentioning. For reasons not dissimilar, the reasons that are similar to why mathematicians love to say that 1 is not a prime number, right? Because it's just annoying if you don't, if you say that it is prime. It's just better to declare a global convention to say that the image of every leg is greater than or equal to itself. So instead of saying that 4 goes to 1, say it goes to 7. Of course, this list of numbers is mod 6 is the same. So I'm not going to strictly talk about permutations. I'm going to talk about permutations which are increasing. And then this label, mod n, gives you a normal permutation. This will be technically useful in a couple slides. Now, I don't have a lot of time, so I'm going to skip over this. There's a big caveat here about, anyway, it doesn't matter. None of those, never mind. Okay, so we're talking, let's say I now want to show you how to take this permutation and how to construct the function directly. And it all follows from a fairly trivial observation, which is that the way of adding a BCFW bridge to a graph acts extremely nicely on the permutation. If you have an on-shell diagram labeled by sigma, and you add a bridge, this permutation changes by a simple transposition. Okay? Now that is kind of a cute observation until you realize that it can be read in the opposite direction. That if you had a function labeled by sigma prime, that it's equal to a BCFW bridge on a simpler graph related by a transposition. And that means that if you just knew the permutation alone and you could decompose it into adjacent transpositions, you would then basically remove all the lines until you just had an empty graph. And so this would provide because the BCFW bridge just adds a single variable every time, this allows you to write down a function that you have. And any way of peeling off adjacent transpositions gives you a representative function and a representative graph. And although any choice would do, for the purpose of the next slide, I'm just going to choose a particular dimension. So let's suppose I emailed you this function. This was the one we saw a couple slides ago. And you didn't know anything about the graph or the function. All you knew was this permutation. Let's decompose it in the following way. I'm going to tell you how to choose which transposition to peel off at every stage. Always choose the first by this ordering, the first pair whose images are ordered. So, all you know about this function is that it's some on-shell diagram where 1 comes in somewhere and comes back out at 3, and 2 comes in somewhere and comes back out at 5, and you don't know what the function is or anything. But you know that whatever this graph is, and whatever this function is, it's a BCFW bridge on legs 1, 2 on a function with this bridge attached. So whatever f naught is that you want is just d alpha over alpha, the bridge, times some simpler function. And this one is bridge 2, 3 on a simpler function. And by this you can keep going until you hit the identity permutation. So by this sequence of things, you can write this, you construct a representative graph that has that permutation label. And this is a representative function in terms of a bunch of BCFW bridges acting on something that should be kind of trivial. What is F8? F8 is an identity, a graph labeled by the identity, and it's this graph without all the bridges. So just delete all the bridges. And this is a weird looking on-shell diagram, but it's not that hard to understand what it is. It tells you all the momentum flowing into the graph is 0. And there's some memory of whether or not something went to itself or itself plus n. This is why I had that convention. So there's some distinction between 1 going to 7 versus 3 going to 3. So which was reflected in the graph by whether it's a white, whether the bottom line is white or blue. Okay. This tells you whether or not saying the momentum 1 is 0 is whether it's lambda tilde 1 that has to vanish or lambda 1 that has to vanish. So this on-shell diagram just tells you that either lambda or lambda tilde vanishes for every particle. Looks like this. Tells you lambda tilde 1, 2, and 4 vanish, and lambda 3, 5, and 6 vanish. Now this set of constraints is nicely encoded by a matrix. Let's just write this system of delta functions by introducing some 3x6 matrix C. It has no parameters. This is not. I'm not introducing any auxiliary crap. This just tells you C dot lambda tilde tells you that lambda tilde 1, 2, 3, and 1, 2, and 4 are 0, and it tells you that 3, 5, and 6 of lambda is 0. So this is just a nice way of writing it. Now, in terms of adding a BCFW bridge, it shifts the lambdas and lambda tildes, which is easy to translate into an active transformation on the C's. So instead of shifting the lambdas and lambda tildes, you shift the columns of the C matrix. So I realize I don't have that much more time, so I'll kind of go through this quickly. But so the first bridge we added between legs 4 and 6 shifts column 6 by column 4 by this new parameter. Anyway, so this operation on building BCFW bridges, you naturally are led to some 3x6 matrix and k by n matrix and Grassmannian. Why is it a Grassmannian? Because these are all linear constraints, and linear constraints always are invariant under GLK. Okay? So that's why it's a GLK invariant. Okay? And we construct some representative matrix involving a bunch of auxiliary parameters. These are the bridge parameters. Now this might worry you, but notice that the number of delta functions never change in this whole operation. BCFW bridges don't add delta functions, they add variables, or integrations. And so you started off with two delta functions per particle, so 12 delta functions, and you keep 12 delta functions as you go. 4 of those delta functions always encode momentum conservation, which means you have 8 left over, which is perfect, because it means that this integral is trivial. You have an integral over 8 parameters, 8 delta functions to soak them up. The delta functions turn these into functions of lambdas, lambda tildes, and you get the function you want. And so, again, we've introduced a bunch of auxiliary things, but they're completely eliminated.
But you still haven't told us how the does get into this game.
Again, so they behave just like the lambda tilde. So it's yeah. I decided not to talk too much about supersymmetry, but for supersymmetry, for n equals n supersymmetry, you'd have a k pi n delta function.
So you just have a super matrix.
This is kind of superspace then.
Yeah. Yeah. But in a more general theory, you just have, well, actually, what would happen is the BCFW bridge is also theory dependent. So in the supersymmetric theory, you just get to write it as d alpha over alpha times an eta integral. But you have some numerators if you did this in pure angles. There's some theory dependence in this little factor here. But this part is theory independent. Okay. Now I wish I had time to talk all about this 3x6 matrix because it is beautiful. And it has some really accidental properties that I don't have time to talk about. For one thing, if you take all the alphas to be real and positive, I don't know why you do that, but if you did, you'd find that all of the ordered minors of this matrix are non-negative. And that means that going from alpha, taking each of the alphas to be 0 to infinity in the positive real axis, you kind of span out some configurations of k-planes, 3 planes in 6 dimensions that always have positive minors. And that means a lot geometrically, which I'm not going to talk about. So if you looked at the geometry of the columns, you could learn a lot. And in fact, actually, the characterization of these matrices is these submanifolds in the Grassmannians, called the positoid stratification, are also labeled combinatorially and are also naturally associated with graphs. And in fact, mathematicians, the mathematics literature had discovered everything about this story, the Grassmannian, the graphs, and these d-log parameters, independently in the mathematics literature around 2006. And it took physicists 4 or 5 years to notice, because they were drawing the same pictures, but they didn't realize there was any physical connection to anything. They didn't care about the functions. They didn't have the delta functions involved. Anyway, so there's a really beautiful story here. But one thing that I want to point out is that if you go up to the top form, so this was, the thing that we had had 8 degrees of freedom, and it's in a 9-dimensional space. 9 because it's 3 times 6 minus 3 squared. So this is a codimension 1 submanifold in the Grassmannian of 3 planes in 6 dimensions. But if we added one more extra bridge, we could get a generic configuration, G36. And it's interesting to note, I'm just going to kind of mention this and then move on, but that the volume form that you get, that this d alpha over alpha, this volume form on in the Grassmannian of 3 planes in 6 dimensions, is exactly equal to the product of all cyclic minors, the 3 by 3 minors of this matrix. And in fact, there's another way we could have discovered the Grassmannian completely independently, and in fact this was how it was discovered historically, was to generalize the Park-Taylor formula. To have a higher k, you need to have higher minors, so you use the generalization of lambda, and this is actually historically how this was discovered. And this continues to be true, meaning that if you go to higher k and n and you do this bridge decomposition, you find that the volume form that we get, this d-log form, which is so nice, is just the product of all the cyclic minors. It's a natural generalization. It's a guess that any graduate student looking at the Park-Taylor formula might have guessed, something like that. Okay.
So you're not doing the integrals here, though,
well, you can do
brands.
You mean for loops? Loops? I basically, this whole half of the talk I haven't mentioned loops at all. It's all tree amplitudes. Yeah. At loops, you have 4 times the number of loop extra integrals to do. And there's a lot of complications and subtleties about choosing the right contours and whatnot. But there is a prescription. So it gives you a concrete answer. And it's in a nice form, so it's just d-log, d-log, d-log. But, we don't actually know how to do those integrals yet. So that's a lot we're still learning how to use these tools. Okay. So how much, do I actually have an hour, or am I overtime?
You are overtime. Yeah.
I'm overtime. Okay. So let me, I'll mention this very briefly. So I haven't mentioned integrability or dual conformal symmetry or the Yangian or any of that other stuff that you've probably heard about if you know about n equals 4. And that's because here it's so trivial that you almost don't even notice it. You see, we have now found a formula for an on-shell function in terms of, that looks like this. It's some wedge of a bunch of d-logs. Actually, it doesn't matter what this looks like. With these delta functions. All on-shell diagrams look like this. And you immediately realize that if you did a diffeomorphism in these auxiliary parameters that left the volume form invariant, this clearly wouldn't change the function. And that's a trivial statement until you realize that an active transformation of the alphas, an active diffeomorphism, can be reinterpreted by the delta functions as an active transformation of the lambdas and lambda tildes, and the eta tildes too. So that means that you can do a diffeomorphism in the alphas, can be reinterpreted as an active transformation of the kinematical data, telling you that there's every diffeomorphism corresponds to a new set of kinematical data that leaves the function invariant. This fact, and because it's diffeomorphisms, it's clearly an infinite dimensional symmetry. And the fact that in n equals 4 scattering amplitudes are invariant under infinite dimensional symmetry algebra was discovered as a consequence of these diagrams. It was not discovered, it was totally overlooked for the 30 years before the BCFW recursion relations were discovered because it's such a subtlety. But it is a very powerful symmetry, and here you almost don't even notice it. It's infinite dimensional because it's diffeomorphisms. And by the way, this statement, the fact that volume-preserving diffeomorphisms correspond to active symmetries of the function, persists for non-planar theories, for n equals 0, for everything. The only question is whether or not the sum of whether or not the symmetries overlap nicely between diagrams. But I would bet that there probably is an infinite dimensional symmetry algebra for our scattering amplitudes and general theories. Anyway. Okay, so let me just conclude with where I started. You have, in a general quantum field theory in 4 dimensions with massless particles, probably those caveats can be removed. You have any network of 3-point vertices can be glued together and represented in this form. And ignore this part, make this part of the measure if you'd like. You get some auxiliary integral over some auxiliary k by n matrix in terms of the kinematical data. And this connection between on-shell diagrams and the geometry on the Grassmannian is extremely rich, and it's been we've learned a lot in both directions. So an on-shell diagram corresponds to some submanifold, some C of alphas, something involving these auxiliary parameters inside the space of k-planes and n dimensions, with some preferred volume form that depends on the theory. And volume-preserving diffeomorphisms correspond to physical symmetries. There are trivial ones that correspond to the square move and that have a very fancy name because they played a really important role in mathematics recently called cluster coordinate mutations. And then there are the non-trivial ones that don't leave the measure trivially invariant. They shift the coordinates, and those correspond to symmetries of the theory, like the Yangian. So in planar n equals 4, we basically know everything. The on-shell physics are described by two colored graphs without any arrows or anything like that. So they're undirected graphs in the plane, and planar. So this is the kind of sets of functions we care about. And the strata that we care about have a special name because they've appeared in the mathematics literature independently. They're called the positoid stratification, and they have a preferred volume form, and it's very easy to write down. And what's amazing about planar n equals 4 is that both sides of this duality are entirely characterized by combinatorics. And so you can associate the left-hand side with just a permutation, and this also characterizes the geometry and everything. What happens when you have, and the physical symmetries have a special name, we call them Yangian. For, say, planar theories with less supersymmetry, you need to just differentiate between the different kinds of particles, whether it's minuslicity or pluslicity. You have these directed graphs. You might wonder how that changes the answer. It turns out for planar theories without supersymmetry, the answer is almost the same. It's exactly the same volume form up to a prefactor that's raised to the power n minus 4. Couldn't be simpler. And this prefactor is often 1. It's 1 in this case. And it depends on the orientations of the graph. And in non-planar n equals 4, you get the same kind of volume forms. We don't know how to characterize these varieties. And the prefactors in the non-supersymmetric theory, again, you can just write them all down. In all cases, it's easy to go from the graph to the function, and to go from the graph to the submanifold and the Grassmannian and all that. That direction is very easy. What remains to be seen, and still an incredibly valuable open questions, is that we still don't know how many prefactors there are like this. How many different decorations of the graph actually change this answer? How many on-shell functions are there in a theory without planarity, or a theory without supersymmetry? Just simple counting questions are still open. And can still actually, we can learn things by just brute force surveys, actually. Because the space of functions remains unknown. The basic question is, how can we invariantly characterize the space of functions, and how does that inform the kinds of functional relations and the kinds of physics questions that we're really interested in? And hopefully, does it provide an answer will it provide a proof to the all-loop recursion relations, for example. Okay, so that's pretty much it. I just wanted to end with some kind of open questions. So there are so many obvious directions to go forward, and many of them I didn't even have time to talk about. But from the very beginning, the most natural question from this talk is just to study this class of functions in a more general theory. We know that this correspondence exists. We just don't know much about how to characterize things, or how to characterize the identities. All the power that we have in planar n equals 4 becomes more complicated. Extending the all-loop recursion relations beyond planar n equals 4. I really should say not extending, but verifying, because the all-loop recursion relations have a clear ansatz. And I think actually this is now out of date, because a few months ago there's been a proposal, been claimed at least that this works for any amount of supersymmetry. Evaluating the amplitudes is a huge open problem that I didn't talk about at all. How do you regularize the integrals? How do you do the integrals? How do you talk about renormalization? Everything. And so far I've talked about unrenormalized sums of Feynman diagrams, etc. And there's a lot of more beautiful things that I should have had more time to talk about considering Yaroslav is here. Like talking about showing that this geometry actually provides a complete picture for what these amplitudes are computing. But I will have to leave those for another day. I'm significantly over time, so thank you very much.
So let me ask you about generality of your statement.
Yes.
First of all, do I understand correctly that you consider only amplitude of massless particles?
Yes.
They are massive
So-
particles.
So the diagrams are completely well defined in theories of massive particles and actually any number of dimensions. But the spinor-helicity simplification and the Grassmannian connection is more subtle. Well, two things change. First is that momentum conservation is no longer linear for massive particles. You can have a non-vanishing 3-particle amplitude. So the spinor-helicity story gets more complicated. But also more importantly, the 3-particle amplitude is not fixed all orders anymore. So the massive 3-particle amplitude gets renormalized. There's a lot of complications there.
What can you say about massless and 5
Um,
in order to talk to massless before?
Yeah, so you unfortunately don't have the spinor-helicity there either. So you don't get this factorization of the amplitudes. But I should point out that there's been some very good work in this direction. So there's a way of talking about spinor-helicity. You can extend this to talk about massive particles and include this. It's worth bearing in mind that the standard model doesn't involve massive particles.
So really you are working with massless particles, but you allow to have massive particles in the CA. It's not a problem.
Yeah, the on-shell diagrams exist. The Grassmannian might be more complicated. I don't know what the Grassmannian story looks like for that. Yeah.
So and in n dimensions you have the same Grassmannian.
The Grassmannian also might depend on 4 dimensions. I don't. So there's a part of the story which is just the on-shell diagrams and what you get diagrammatically for the recursion relations, and I think that has to work in all theories with massive particles in any number of dimensions. It's definitely true for tree level amplitudes. But the connection between these diagrams and the Grassmannian is really only precise today for 4 dimensions and massless particles. They probably can be generalized.
Is there a bot periodicity?
What?
Is there a bot periodicity? Like mod 8, like how spin is a...
Yeah, so you could go to... so if you have...
12 is the next best.
Yeah, there are definitely useful generalizations of spinor-helicity, like in 6 dimensions, that have a similar story. And 3-dimensional theories also have a nice restriction here. It's a little bit odd because 5 is harder than 3, but so ABGM also has a direct connection. Yeah. But just to avoid saying anything that's wrong, everything is strictly true for planar, for massless theories and formats, and probably true in more general. Yeah.
So in that context, if a massless 4-dimensional theory, can it live on a curved space, or it has to be on a flat space?
Well, the amplitude, so spinor-helicity, yeah. So as long as you have asymptotic flatness, you can talk about, you have nice twistor variables, and I think a lot of the story has to go through, but I don't know the details.
But you could include spin 2 massless.
Oh yeah, yeah.
And then treat Broadening's graduation.
Absolutely. In fact, yeah, there's no difference. I gave the general formula for all helicities, including H+2.
Do I understand correctly that the contribution of massive particles in your stuff is simply a factor, simply a constant factor, or whatever?
So, sorry, massive particles again.
So you have massless particles.
Yes.
But you have said that you can have massive particles in the CA. And
Yes.
still you have the same answers.
No, it's
but
a-
probably not precisely the same, but probably it is only a constant factor depending on them, or what can depend on this massive particle for sure.
So you find some interesting things. So for example, for massive QED, if you look at the massive 3-particle amplitudes, instead of getting a unique function, if you include the masses, you get a sum of 2 different functions. So there's also kind of a unique answer. They can also get renormalized. But just to the leading order of perturbation theory, the rational part is fixed by one relative number between them. And for QED, this one number that tells you the difference between the two is just G minus 2. And how it gets renormalized is how you get loop corrections of it. So it's a little bit more subtle because there isn't a single function for the 3-particle amplitude, but it's a sum of 2 functions. So you can feed that into this machinery pretty straightforwardly, but you get a 2 to the number of vertices extra terms. I'm not sure if I answered your question, but
So if I have some physical calculation and I know how to do it in terms of Feynman diagrams, let's say, is there a simple algorithm for just converting it into a sum of these type of diagrams, or is it more subtle than that?
well, I don't know why you'd want to convert it. It's easier to do it in this direction. At tree level, it's diagrammatically it's what we have here basically. You have these factorizations evaluated with this. It comes from Cauchy's theorem. And that gives you some number of terms. It gives you a fixed number of terms. It's a combinatorial thing. It's much fewer than the Feynman diagrams.
So approximately, is the answer just a reroute contours?
A reroute.
You analytically continue, move the contours around, and
It's a little
you
bit.
get the Wills expression.
Yeah. It's a. Well, at loop level, there's a contour thing. Already at tree level, there's another subtlety which is worth bearing in mind, that the denominators, the poles of the Feynman expansion are all physical. They're all sums of momenta squares. The recursion relations give you complex shifted momenta in the denominator. So you have spurious poles. And as a rational function, these things cancel. So between different terms, you get cancellation. But the fact that there are spurious poles, that there are things in the denominator which can't come from the Feynman expansion, means that individually the terms that you get in the recursion relations are not partial sums of Feynman diagrams or anything like that.
Right. But if I guess what I'm saying is, okay, so there shouldn't necessarily be any mapping between this Feynman diagram and this.
No.
But if I'm calculating something physical and I know how to do it as a sum of all these Feynman diagrams, you might imagine that you want to say, okay, that's too complicated. I want to calculate that same physical quantity. Which of these diagrams do I have to use? Is that understood?
Yeah, it's just using a recursion relation.
Okay.
It generates a specific set of diagrams.
And how precise is invariance with respect to well-preserved differentials?
So
Is
it's
this in some
Yeah, so
approximation?
this is a great question. So at the level of an individual on-shell function, so just a single diagram, this is just infinitely robust and it's clearly infinite dimensional, and there's really no question about it. I mean, it's you know everything, and it's on very firm ground. But the subtlety comes about because amplitudes are not single diagrams, but they're sums of them. And so to wonder, the question you really care about is whether or not the scattering amplitude is symmetric under these transformations. And to do that, you have to care about how to match the volume-preserving diffeomorphisms of this graph with the volume-preserving diffeomorphisms of the next one, etc. And you have to make sure that they have some overlap. Now, my intuition, the reason why I'm very confident that something is going to survive is just because wouldn't it be surprising if a lot of infinite dimensional symmetries didn't overlap, but on at least an infinite number of dimensions? But I could be totally wrong about that, and you might not have anything that survives. So you might have lots of term by term that have infinite dimensional symmetries, but no symmetries preserved by all of them.
Yeah, but these terms are precisely symmetric. This is not an approximation.
No, yeah, exactly.
Yeah, are you saying whether it's a degree of symmetry with the entire S matrix?
Yeah. Yeah, the on-shell diagrams will have these symmetries, but whether or not the S matrix does is more subtle. And we don't know how to answer that yet.
So if you did, you typically have an idea what they would do?
That's a great question. I have some conjectures, but I have speculations. So there's also recently been identified a proposal for infinite dimensional symmetries of S matrices in general for massless
It's
particles.
the MS business.
Yeah,
So do people think that's connected or not?
I think it's connected. In fact, maybe, I don't know, but there's a lot of speculation there. For one thing, it's really hard to see how the BMS group is related to the Yangian for planar equals 4. It doesn't really care about planarity in any way. But if somebody came back tomorrow and showed you how these level operators that you get in on the holomorphic side, or these holomorphic and anti-holomorphic generators correspond to the level generators in the Yangian, I wouldn't be surprised. No. But the fact that the BMS group is probably a symmetry, probably provides you an infinite dimensional symmetry for general quantum field theories, is a reminder to everybody that infinite dimensional symmetry doesn't mean integrability or much. Yeah, so it's another question. Doesn't mean that it's useful.
All right. Well, let's thank Jake again.